Okay, we're going to take a look at lesson 4, which is another day on exponential growth and decay word problems, which is really a review of our day 3 where we first started to look at what growth and decay looks like in an application sense. So what I'd like everyone to do is take a moment to read through the warm-up. Just pause the video for a moment so you can read through it and try to fill in those 4 values for D, and then we can go over it together. So this question is talking about water draining out of a pool. They tell us that the depth of the water is decreasing at a constant percent rate of 20% an hour, and this is the equation that's modeling that. Find in depth in feet, D, to the nearest tenth of the water in the pool after each of the following times T. So let's just look at this equation for a moment. Here we have D equaling 12 times 0.8 to the T. So if we think back to the standard form of an exponential function, the 12 is really our y-intercept, which in this case, the initial amount would be the depth of the pool. So the initial depth of the pool must be 12 feet. And then B, the multiplying factor, is 0.8. So right now, if you went to your calculator and you typed into your y equals, I'm just going to write this down here, typed into your y equals 12 times 0.8 to the x, and then looked at your table, you're going to look for the values that are next to 1, 2, 3, and then there is a big jump down to 20. So you should be getting values for y, which in this case is my D, my depth, of 9.6, which means after 1 hour, we go from a depth of 12 feet initially to 9.6 feet, then down to 7.7 feet after 2 hours, 6.1 foot after 3 hours, and then only 0.1 or a tenth of a foot after 20 hours. So the pool is almost empty at that point. Okay, so what we really want to talk about today is how you know when something is growth or decay and what you do with that rate. So if you look at this equation, they don't actually use, or I shouldn't say they don't use, you don't see this 20% number in this equation. So let's remember where that came from. So if we come down here a bit to our exponential growth and decay formulas, I do notice they're both written in terms of subtraction. So could everyone just please turn this minus sign into a plus sign in their notes? Because that's the one for growth. That should be a plus. And then exponential decay has the minus. So I'm actually going to use the decay, and then we're going to go back up to the warm-up in a moment. But let's just talk about the parts. So A is our total amount. So that would be like our D, the depth of the pool over time. P was the amount present at the beginning. So that was our 12 feet. R was the rate. So that's what I didn't actually see in my equation up here. I just saw the 0.8. I actually saw the number after the subtraction was done. So let's come back here for a moment. I just want to break this formula down a bit. So if I went back a step and I showed the 20%, which in decimal form would be 0.2, and I showed that that rate was being decreased from 1, since that's what we do when we have a decay rate, this is the breakdown of this formula. That 0.8 came from subtracting 0.2 from 1. So with decay, you don't always see the rate. Sometimes you have to think about it. If I had taken 1 and subtracted the 0.8, I could have found their difference. And that's another way you could kind of go backwards and find the rate. What was subtracted from 1 to get me that 0.8? And that was the 0.2, which was the 20%. Okay, so let's take a look at this. So when we have growth by a percent, we add that percent again in decimal form to 1. We raise it to the time period, and then we multiply it by the initial amount, which sometimes we refer to as P, the amount present in the beginning. And then the only difference, if we're decaying or decreasing by a percent, we subtract that decimal form of that percent from 1 instead of adding it. So if we take a look at example 1, they want to know, is this equation, which they're giving us here as A equals 21,000 times 1 minus 0.12 to the T, is it a model of exponential growth or decay? So everyone take a moment to think about that. And this should be modeling decay since we're subtracting the 0.12. Then they're asking us, well, okay, then what is the percent change? So the percent change we can see right here. It's the 0.12. That's the rate being subtracted from 1 to show us this exponential decay model. So we're definitely looking at decay, and we're looking at a decay rate of 12%. Now, this other choice that had decay, that 0.88, where that's coming from is if you actually typed these numbers into your calculator and subtracted 0.12 from 1, you would get 0.88. So that's not the rate, that's actually just the multiplying factor. So those are not the same thing. The multiplying factor is what you're actually multiplying your y values by if you were looking at this table, whereas the rate is what you subtract from 1 to get your multiplying factor. Okay, let's keep going. Take a moment and read through number 2. So we're told that Mr. Smith invested $2,500 into a savings account that earns 3% interest. Compounded annually just means it earns this every year. They made no more deposits or withdrawals, so the money of $2,500 is still there. Which expression could be used to determine the number of dollars at the end of 4 years? So again, we're going to be growing. That's the difference from example 1 and example 2. We're growing by some rate. So the initial amount we have is $2,500. We're growing at a rate of 3%. So let's just think for a second. 3% in decimal form is 0.03. And then the time they told us was at the end of 4 years. So 2,500 is the initial amount. 1 plus 0.03, raise it to the 4th. That's going to give me choice 1. Okay, last example together. Sam bought a used car for $8,000. He boasted that he got a great deal since the value of the car 2 years ago when it was new was $1,500. So let's just say that's the initial amount of the car, right? His friend Derek was a little skeptical, stating that the car's value typically would depreciate by 25% a year. So Sam got a bad deal. So Derek's a little skeptical, doesn't think the $8,000 car was a good deal. So use Derek's logic to write a formula for the value of Sam's car. And they want you to use T for the total age of the car in years. So I want you to think about this for a moment. If you have to reread it, pause the video and see if you can come up with the correct equation. Okay, so I'm going to use Y. You could use A also. I'm going to take 15,000. That's the initial amount of the car. Depreciate means decrease. So Derek thinks that the car depreciates by this 25% a year. And they said we can use T for time in years. So this would be the equation. Again, you could have used an A instead of Y, but that should have been the setup. You have your 15,000 is the initial amount of the car 2 years ago. 1 minus 0.25 because we're depreciating or decaying at a rate of 25% each year, and they told me to use T for the years. Now we have to determine, well, who's right? Did Sam get a good deal, or does Derek correct? Did Sam not get a good deal? So Sam bought the car for $8,000 after 2 years. So now let's see if this is a good or bad deal. So let's take our $15,000 initial amount of the car, take the 1 minus 0.25 and raise it to the 2, since that's how much money we're trying to analyze. How much was this car worth after 2 years? If you type this into your calculator, I'm going to round to the nearest cent, $8,437.50. So now we have to think about this. If Sam bought the car for $8,000, but it's really worth $8,437.50, that means Sam was right. He got a good deal. And it says to justify, so I'm just going to say, well, $8,000 is less money than $8,437.50. So Sam got the good deal. He saved about $437.50. Okay, so now what I want everyone to do, if you want even here, this is again supposed to be a plus sign. There are a couple practice problems for you to try, also going through all this growth and decay application questions. We're going to post the notes to this lesson on Canvas like we would on a normal typical school day. The answers to all the practice problems will be on Canvas as well as the lesson that we just went through together. And we're also going to start asking you to submit your homework. So the 11-4 homework, we're going to ask you to submit online. We're going to post directions and exactly what we expect of you on Canvas either later today or early tomorrow. So we will update you with that very soon. I hope you're all doing well, and we'll talk to you soon.